we are talking about relative atomic mass, and we are saying relative atomic mass is simply the average mass of an atom compared to 1 over 12 the mass of carbon. Relative atomic mass is the average mass of an atom compared to 1 over 12 the mass of carbon. So I was saying the very mass that we are able to see on the periodic table, that one which is given on the periodic table, that is what we call relative atomic mass. For example, if you talk of hydrogen, the relative atomic mass is about 1.00 something there. If you talk of carbon, that's 12.01. Please, if you're not speaking, you can just switch off the mic. All right. Now, having said that, since we know where we can find the relative atomic mass, there is also what is called relative formula mass. Some people would write this as M with R, others will write two capital M's. It's up to you. And then there's also what is called relative molecular mass. So when you're talking about relative formula mass, it's simply the masses in a compound which are added together. And when you're talking about formula mass, it should be an ionic compound. For example, when you talk of sodium chloride, you have got sodium chloride. This compound is an ionic compound because you've got a metal and a non-metal. So when you get the relative atomic mass for sodium, and you get that is about 23, and you get the mass relative atomic mass for chlorine, that is about 35.5. When you add these two masses, the answer that you are going to get is called relative formula mass. Now, when you are talking about relative molecular mass, it's just the same thing as relative formula mass, but you are just talking about molecules. So molecules are made up of non-metals. For example, water. When you find the mass of oxygen, of course, that is about 16, and then you've got two hydrogens here, and each hydrogen has got a mass of about 1. So when you total this, what you are going to get is a relative molecular mass. Why? Because water is a molecule. But when you get to add the masses in sodium chloride, that will be relative formula mass. Why? Because we're talking about an ionic compound. So basically the same thing. Relative molecular mass is the total relative atomic masses in a molecule, and relative formula mass is the total relative atomic masses in an ionic compound. Am I too fast? Is that fine? Okay, so we are saying relative formula mass is the relative atomic masses in an ionic compound, and relative molecular mass is a total or the sum of all relative atomic masses in a molecule. So when you add the atomic masses in a molecule, you are going to get the relative molecular mass. If you add these same atomic masses in an ionic compound, you are going to get relative formula mass. Is it okay? Now, how do we calculate relative atomic masses? So before we get to calculate that, we need to understand something called isotope. And just a reminder, who can explain for us what we know? What is an isotope? What is an isotope? Anyone? If you know the answer, you can just speak it out. Yes. I saw someone raise the hand. You can say. Okay. Atoms of the same element having the same mass number. sorry, having the same proton number but different mass numbers or different neutron numbers. Remember, when you want to get a mass, you add the protons and the neutrons. So if the neutrons are different, obviously even the mass is going to be different. So atoms of the same element having the same proton number but different mass numbers, those are what we call isotopes. Now, just from isotopes, this is where we calculate the relative atomic masses, just from the isotopes. So how do we get to calculate the relative atomic masses? So for example, we are saying atoms of the same element. You can have an element such as carbon. You have got carbon, you have got carbon 12, you have got carbon 13, you also have carbon 14. This is the same element, but you see these are different atoms. Why? Because they've got different masses. So their proton number is all the same. They have got all 6 protons. All that is different is the number of neutrons. Because the number of neutrons are different, therefore even the mass numbers are also different. So these are what we call isotopes. You can see all these numbers are the same, but on top the numbers are different. Now, how do you get to calculate the relative atomic mass of an element? I'm going to give an example of some, maybe 2 or 3 elements, how to calculate the relative atomic mass. Now, before you understanding how to calculate the relative atomic mass, you need to understand something which is called the percentage abundance. When you are talking about percentage abundance, all you are talking about is if you get a sample of this kind of element. Remember, we are talking about isotopes, atoms of the same element. So if I get a sample, maybe for example of carbon, I've just gotten a sample. I don't know. I didn't want to get carbon 12 or carbon 13. It's just a sample. How much of carbon 12, carbon 13, carbon 14 am I going to find? Just in any sample that I get. So for example, if you get 100 grams of carbon just at random, you might find that from that 100 grams, maybe 50% is carbon 12, and then 30% is carbon 13, and then 20% is carbon 14. If you add these percentages, you should get 100. So that is what we call percentage abundance. Just how much in a sample picked at random are you going to find that amount of element? So now that we know what percentage abundance is, we can now look at calculating relative atomic masses. For example, let's talk of bromine. Bromine atom is available in the form, and you are going to find it in a form of isotopes, and there is bromine 79, and the percentage abundance when you just pick it at random is 49.7%. And you also have, let me also put the proton numbers 35. You also have bromine 81. The abundance for this one is 50.3%. The proton numbers are all the same. So when you get a sample of bromine, you are going to find bromine 79 and bromine 81. Now the question is calculate the average atomic mass or the relative atomic mass for bromine. So how do you go about it? How do you get to calculate the relative atomic mass of an element? Actually, those values which you see on the periodic table, those are relative atomic masses. So there are different elements which were gotten, and then this same formula we are using was used to find now the mass that you can see on the periodic table. So relative atomic mass is given by mass times percentage abundance plus second mass times the second percentage abundance. If there is another one, you continue like that. It doesn't matter how many atoms are in that element. So all you get is just to add them. Now in this case we only have two. If you add this percentage and this percentage, you should be able to get 100. And you can prove that 49.7 plus 50.3, that is going to give you 100. So it's the same. If they just give me this percentage and then they tell me that there's also another mass, that should mean if I add those two percentages I should get 100. So the missing one, I can easily find it. So in bromine, in this case, the first mass is 79, and then I'll multiply by the abundance, percentage abundance. How abundant is that? That is 49.7%. But I'm going to express that number as a decimal. So 49.7% is the same as 49.7 over 100. And then I'll add the other percentage is 81. And then I'll multiply by the abundance, that is 50.3. Now divide that by 100. So make sure the abundance we're multiplying by is a decimal, not a percentage. That's why I'm dividing by 100, because a percentage is always out of 100. So we're going to perform these calculations. That is 79 multiplied by, well, when you say 49.7 over 100, that is just 0.497. You can punch on your calculator. So 79 multiplied by 0.497, and then plus, that is 81 multiplied by, if you again divide 50.3 divided by 100, that will be 0.503. So that is going to give us 80.006. This is the mass, or the relative atomic mass, for bromine. Let's see what is given on the periodic table for bromine. Okay, so bromine is here. It has been given as 79.904, which is basically 80. So this one is written to a lot of significant figures and a lot of decimal places. That's why you see it is more accurate. So that is 79.9, which is just basically 8, as you can see here, 80.006. So that is how you get to calculate the relative atomic mass of an element. Do we have questions before we go to another example? So when you want to calculate the relative atomic mass, I'll repeat, you get the mass of the first element multiplied by its percentage abundance, and then plus the mass of the second element multiplied by its percentage abundance. If there's another one, continue like that. So in this case, you can see that these numbers are the same. Obviously they are not masses because they are isotopes. These are proton numbers. So the mass says, you get the mass, that's the 79, multiplied by the abundance, which is this one, but express it as a decimal. So you always divide by 100 because it's a percentage. And then again get the other mass, which is 81, multiplied by the abundance, which is 50.3. Yes, you always be given. If they have not given you, then the question will be asking for you to calculate the abundance. They will give you the other data that is required. Do we have any question? Any question? All right, let's look at another example. Yes, go on. Pardon? Mm-hmm. It's not always two elements. Let's consider this example. If you talk of iron, it's just that for bromine there are only two isotopes. That's why we use two. But if you talk of elements such as carbon, hydrogen, those have got three isotopes. So let's say for iron, we've got iron 54, and the abundance is 5.95%. And then there is also iron 56. the abundance is 91.88. And then we also have iron 57. And then the abundance for this one, let's say they've not even given us the abundance. Now the question is, calculate the relative atomic mass for iron. So to be able to calculate the relative atomic mass, all you are going to do is relative atomic mass is given by the mass, the first mass times the first abundance, plus the second mass multiplied by the second abundance, plus third mass multiplied by the third abundance. So depending with how many you have. Yes, there is a question, Pagsina. All right. Now that we've written the formula, and then we are going to get the mass for the first atom, that is 54, multiplied by the abundance we can see is 5.95, that is a percentage, so divide by 100. And then plus we're going to go to the second mass, that is 56, the abundance, that is 91.88, divide by 100. And then the other one is 57, the abundance, well, we don't know the abundance. All we know is that when we add the abundance for this one plus this one plus this one, we should get 100. So what we are going to do is we'll say 5.95 plus 91.88 plus, let's just call it x because we don't know the abundance for this one. That should give us 100. So to remain with x, we'll say 100 minus, we'll take 91 the other side, so it becomes negative. And then we also take the 5, it also becomes negative. Therefore, x is going to give us 2.17. That is going to be the abundance. So we'll put there 2.17. This is also a percentage, so divide by 100 also. So you can just work out that now on a calculator. If you get to punch what we have here on a calculator, we are going to find 55.90. That is the relative atomic mass for iron. We can see what is given on the periodic table. Okay, so iron is here. That is 55.845. 55.84. So this is 55.90. The difference is just because this one is a practice question and perhaps we've not used the actual percentage abundance, so that is why. So is there a question anywhere? Is there a question anywhere before we get to look at another one? The last one in this case. Alright, what of if you've been given already the relative atomic mass, you've been given already the masses, but they ask you to find the percentage abundance. How do you go about it? So let's consider an example that is going to talk about that. Let me just get a question, something like that. Okay, there's a question here. The average atomic mass of a sample of an element. So we have got an element X. This is an element X. And its relative atomic mass, or the average atomic mass for this element, is been given as 16.2 atomic mass unit. So when you talk of atomic mass unit, this is just a unit that we get to use to calculate the relative atomic mass. And the atomic mass unit, one atomic mass unit, if they give you the mass in atomic mass units in chemistry, you want maybe to calculate something, you don't use this one. The SI unit for mass is a kg, so you need to convert this value to kg. And one atomic mass unit, the value is going to be given, the conversion factor. Let me just see if I can get that one. Okay, one atomic mass unit is equal to 1.6606 times 10 to the power negative 24 grams. Where does this come from? We have got what is called the Avogadro's constant. So one atomic mass unit is simply the Avogadro's constant, which is 6.00022 times 10 to the power 23. This number just raises to the power negative 1. That is going to give you the conversion for one atomic mass unit. And it will be given in a paper if there is need for you to do the question. Okay, so we are saying the average atomic mass of a sample of an element is given as 16.2 atomic mass units. And then what is the percentage of isotopes? So this is the relative atomic mass, but this one has got isotopes. The first isotope is X16, and then the other isotope is X18. So what will be the percentage abundances if we know the relative atomic mass already? Remember, how do we find the relative atomic mass? Relative atomic mass is given as the first mass times the abundance plus second mass times the abundance. Now the relative atomic mass we've already been given, that is 16.2 atomic mass units. And that is going to be equal to the mass of the first isotope, that is 16. Do we know the abundance? We don't know. Now the thing is this, if you know the abundance for this one, let's say the abundance for this X is Y. What will be the abundance for this one? Remember, the abundance should give us 100%. So if this was in percentage, if this one is Y percentage, then what will be this one? How do you find it? So Y percentage plus another one that is missing should give us what? 100%. Meaning I'm going to take this percentage that side. So if this one, the percentage is Y, then this one is going to be 100% minus Y percent. Now if I don't want to work in percentages, we actually use decimals when we are using here. Remember, I was dividing by 100%. So if something is adding to 100%, as a decimal, 100% is 1. Remember, 100%, if you want to convert to a decimal, it is 100 over 100. So if this one, the abundance is Y, then to find the abundance for this one, we need to say 1 minus Y. This is going to be the abundance, such that when we add Y plus 1 minus Y, this is negative Y, this is positive, they are going to cancel. That will just give us 1. And 1 as a decimal is 100%. Does that make sense? So if 1 is Y, then another one is going to be Y, 1 minus Y. So that when you add the two abundances, you should get 100% or 1 in decimal form. Does anyone have a question on that? So you have got two things. The abundance is going to add up to 1. You've got two percentages. For example, if you get 60% in a test, then you've gotten 40% wrong. And 60% as a decimal is 0.6. So if you have got 0.6 in a test, then you have got 0.4 wrong. How did you find the 0.4? You said 1 minus 0.6. Or how did you find 40? You said 100 minus 60. So in percentage, you're going to subtract from 100, but in decimals, you're going to subtract from 1. So if you know Y, then to find the other one, just say 1 minus the same Y. Is it okay now, or there's still need for clarity? Is it okay? All right. So now this mass 16 is related to the percentage abundance Y. So I'm going to multiply 16 by Y. If you swap them, then you are wrong. And then the second mass, that is 18. And then its percentage abundance is what? 1 minus Y. So our aim is to find the value for y. So this is going to be 16.2 being equal to 16y, and then plus I'll multiply 18 times 1, that will be 18, and then 18 times negative y, that will be 18y. I'm going to take like terms to the same side, so I'm going to get this value and take it this side, so it becomes negative. That is going to be 16.2 minus 18, and that is going to be equal to 16y minus 18y. So we'll just get to subtract 16.2 minus y. I mean minus 18. So that is going to give us a negative 1.8. And if we subtract 16y minus 18y, that will give us negative 2y. So we divide both sides by negative 2. So if we divide this one, we cancel with this one. Therefore, y is going to give us, let me just punch that again on my calculator. Negative 1.8 divided by negative 2. Okay, so that has given me 0.9. So this 0.9 is as a decimal. How do you convert a decimal to percentage? Just multiply by 100. Just like when you are coming from a percentage to a decimal, divide by 100. So this is going to be 90%. So the one which is 90%, and don't confuse them. So the x is 16 has got 90% abundance. So if this one is 90%, how do you find the other one? To just be 100 minus 90, since we are saying it's 1 minus y, so it will be 1 minus 0.9, which is 0.1, and 0.1 is the same as what? 10%. So 1 is 10%, 1 is 90%. Don't confuse these two. Remember y, the y we have calculated was applying to the one which was 16. That is y. So we've calculated y to be 90. Therefore, the 16 one is the one which is 90. Don't confuse those. So does that make sense? Does that make sense? Or someone is left out somewhere? Yes. Anyone left behind? Okay, it seems we are. Yes, please go on. It doesn't matter as long as you are going to know which one you've given y, which one you've given y, 1 minus y. It doesn't matter which one you give. It's your choice to make. Okay, now that we know how to calculate the relative atomic mass, let's look at something very interesting, and then that will be it. And if you miss this portion of chemistry, these carry a lot of marks, big marks, so don't miss. Let's look at percentage abundance, and then just look at empirical formula and molecular formula. That will be it. How do we calculate not percentage abundance but percentage composition of an element? So calculating percentage composition. Let's say, for example, we've been given an element or a compound that contains some elements. Let's say the compound is calcium carbonate. You want to find the percentage composition of carbon in calcium carbonate. How do you calculate that? So what you are going to do is just get the mass of carbon. So the percentage composition for carbon is going to be the mass for carbon divided by the mass of the whole calcium carbonate. And then the answer that you get multiplied by 100. That is how you get the percentage composition. So in this case, carbon will check on the periodic table. Carbon has got a mass of 12.0107. And then we're going to divide by the mass of calcium carbonate. We'll check on the periodic table. So oxygen on the periodic table, we have got first three oxygens. We are going to multiply the mass of oxygen on the periodic table. Let's see. That is 15.9994. And then carbon, we only have one carbon in this compound. And then multiply by the mass of one carbon, that is 12.0107. And then I've got calcium, we only have one calcium here. So 1 times, we get a molar mass of, and that is 40.078. So what we are just calculating here is the relative formula mass. When you get to add the masses together, you get the relative formula mass. So you can work it out if you've got a calculator where you are. You can tell us the value. 12.0107, and then plus 40.078. Okay, so that has given me 100.0932. So this is the mass of calcium carbonate, 100.0932. And then we're going to multiply by 100% to find the percentage for carbon. So that is 12.0107 divided by 100.0932, and then multiply by 100. So has anyone found the answer? If you've calculated, you can just tell us what you found. So it's about 12 point. What have you found? Okay, 11.995. That is approximately 12%. So this is the percentage of carbon in this compound. If you want to calculate the percentage of oxygen, just get the molar mass for oxygen. What's the molar mass for oxygen? Remember, there are 3 oxygens in this compound, so you are going to get this value, and then you divide by this one, and then multiply by 100. So that is how you get us